Hi class, welcome to Refrigeration and Air Conditioning lecture number 1. So this will be on history and applications of refrigeration. Now, before we get into the details, let's go through a basic definition of what refrigeration means. So refrigeration is the process of removing heat from a space, substance, or a system to lower its temperature below the temperature of its surroundings, also the temperature it had before. And it also requires you to be able to maintain that low temperature and have a temperature difference between the space or the substance you're trying to cool from its surroundings. Now, what does the process of removing heat mean? What exactly is heat? Heat is basically the transfer of energy. So let's say we have a system or a space where we are trying to induce a refrigeration effect. So let's consider the space. It also has some surroundings. Let's assume they were at two different temperatures or the same temperature in the beginning. So the surroundings were also at 25 C and the space is at 25 C. Now if I have to create or you have to create a refrigeration effect in this space, what that means is we are removing heat from here. Okay, let's call this heat removed as Q. When you remove heat, what happens is the thermal energy drops and the temperature drops, and let's say it goes to a final temperature of 18 degrees C. Okay, so you're removing this heat and you're probably transferring that heat to the surroundings, which is at 25 degrees C. So the process of moving heat from a space or substance and making it colder and probably simultaneously taking that heat and passing it on to a warmer object or making something warmer is uh, typically what it means to be a refrigeration effect. Okay, so normally heat would like to go from a high temperature to low temperature, right? Your coffee cup, if you place the coffee in on your table, it tends to cool down. So heat normally goes from high temperature to low temperature. The coffee loses heat to its surroundings, right? Here, the heat has to go from a colder object, let's say in 18 degrees C, to a warm object to the surroundings. So the refrigeration effect is a little bit tricky. It is counterintuitive, and it's not very easy to um, um, induce in real life situations, right? It's easy to heat something up, but think of how many ways you can cool something, right? So hold that thought. Let's try to understand how people historically try to cool things and create this refrigeration effect. So if you look at the timeline of refrigeration and air conditioning, we can slice it in different ways, but one way to do that would be into these three different sections, okay? Before the introduction of mechanical refrigeration and the period of mechanical refrigeration, which is really short period, and the current generation, which is the electrical refrigeration period, which happened since 20th century. So if you look here, even though the refrigeration effect is not so easy to create, that effect is not so easy, people have been using it several hundred years before Common Era, right? Um, so how did people in those historic times create this effect? Uh, you should do this as a thought exercise. If you don't have any machines or electricity, um, how do you how can you think of creating a cooling effect on yourself? One option would be, one easy option you can think of is if your hand gets wet, for example, and there is a little bit of breeze or wind of air movement, you can feel that your hand suddenly feels cold, right? So what happens is water evaporates from your hand and you feel a cooling effect, right? So that evaporation of a volatile liquid, it doesn't really need a mechanical device, right? You can put some water in your hand and it evaporates and gives you some cooling effect, right? So evaporation of a volatile liquid. The other is, for some reason you found some colder object than your surroundings. For example, you had some ice um, outside your house in winter, and you can bring that ice or snow inside the house, and you want to feel a little bit colder, you touch it, right? So touching or contact with a colder object, right? So primarily, this is the method that people in the historic times um, relied on. But they also had some other cool tricks. So let's look at what they did. The first one, um, the contact method, what they did was, okay, they stored the ice and snow. In winter, you don't really need cooling inside your house. It's already winter, right? So what you do is you store them for future use. So you get the ice and snow and then put them in insulated storages, okay? And if you put a lot of ice and store it inside insulated storages, you can last from winter to the summer and for throughout the year, actually. So if you collect enough and store it in large storage houses, there's enough thermal inertia there that you could save it for a long time, right? So what people did was they created these ice houses, okay? And then whatever they store, it's like storing grains during the harvest season and then using it later. The same way they stored ice during the winter season and used it later. Okay, so the technology was mainly about how to create good storage houses, and um, there are several uh, old designs. One of them, this is a image of a storage house that was in Iran, and they called it Yakshal, and this is recorded in 400 BCE. Such designs. Okay, so a lot of them are built with mud houses, and they're dug in deep inside the earth, and the ice may be stored at the bottom layer. Okay, so it's away from the heat of the sun, and whenever you need ice, you come down here and take it. They also use additional cooling effects similar to what I just mentioned, the evaporative cooling and radiative cooling, which we'll get to in a second. Okay, so such storage was one of the first ways where they used this ice to create deserts and frozen treats throughout the year. Okay, so that was a cool trick that our forefathers did. Um, the other method was nocturnal cooling. What is nocturnal? Nocturnal means night, right? Happens in the night. What happens in the night that helps with ice making? So this is especially true if the night sky is clear. Okay, so if the night sky is clear and you have a dry weather, then you have a big chance of creating radiative cooling. So what happens is um, the upper layers of the atmosphere and the space is at a considerably lower temperature. So let's say an equivalent temperature for the space, you could think of it as minus 20 to minus 50 degrees C, okay? Um, and if you have done a course in heat transfer, you know the radiative heat transfer is the equation is something like this, right? Sigma epsilon area and temperature of, let's say, the object to the power of 4 minus, let's call this space to the power of 4. All right. So because the space is at a much lower temperature and the object, let's say in our case, is water stored in a small vessel, let's say it's at 18 degrees C. So it can, based on this equation, it can cool down to below 0 degrees C. Okay. Because there is enough heat transfer occurring throughout the night. Um, However, what they needed is carefully placing the insulated vessel and the amount of water that you're spreading over it. So if you have an insulated vessel, um, what happens is you're able to create this refrigeration effect of removing Q from this water. At the same time, the insulated um, vessel reduces the Q from the surroundings that will heat up the water. Okay, so the Q space dominates, and you're able to drop this temperature below 0 degrees C and freeze the water and create ice. So if you don't have this insulated vessel, you use, let's say, metal vessels, um, you will not achieve that rate of cooling. And the other thing is you want very thin layer of water, roughly 3 centimeters or less. So if you have clear night skies in your area, you could try this experiment. Um, it may be difficult in Thailand because of the humidity here, but if it is a clear, dry place closer to the desert, it is very common in the historic times to create ice using this method. Now, the other method, which we have discussed already, is the evaporative cooling of a volatile liquid. And the volatile liquid in the olden times was primarily water. So people used to store water, just like the ice making method. Uh, they used store in earthen pots or houses. The roofs of the houses can be cooled using wet straws. Okay, so as the water cools or water evaporates, it creates a little bit of evaporative cooling. And we'll go into more details on the actual science and physics in the upcoming classes. Uh, but what I wanted you to get to is the science or the scientific effects that are at play here. Evaporative cooling, radiative cooling, and then in this case, direct contact with the ice and snow using insulated storage. The fourth method, which happened closer to the 18th and 19th century, was, I don't know whether you're familiar with, you know, lakes and ponds and streams freezing in cold countries during winters. All right. Of course, you have seen the frozen Arctic and Antarctica and all that. So the ice blocks, right? In winter, a lot of countries in the northern latitudes, um, they have lakes that get really frozen. So during the 18th and 19th century, this became a business where Mr. Frederick Tudor, he used to be called, he was known as the Ice King. He created this business idea of cutting this ice, storing it, and transporting this internationally all over the world in ships and barges. And people are able to enjoy ice even in really hot and arid countries. So the thing to understand here is most of these ships travel for months, right, to reach the other continent, and they are still left with enough tons of ice that this business was viable. And this business only began to drop after the introduction of mechanical refrigeration, right? So up until mechanical refrigeration, um, the ice was available all over the world thanks to this ice trade, right? Uh, if you had money. All right. So these are some pictures of cutting thick blocks of ice. You can see this is almost 2 foot or 3 foot thick block of ice being cut from some lake. I believe this is Lake Michigan. Um, and then took on a vehicle for transporting it worldwide. Now, so far, all the methods are considered pre-mechanical refrigeration. So what created the onset of mechanical refrigeration? Um, you can see here this term. So the start of mechanical refrigeration, one thing that you can look for is the aspect of using mechanical methods to create the refrigeration effect. Okay, so also previously, most of uh, the working fluids used was water, right? You either water evaporating, water radiatively cooling, cutting a block of ice, or storing ice from the winter. But now, in addition to using mechanical means, um, there was also uh, an interest or a development of using other um, working fluids, right? So the first mechanical refrigeration system can be attributed to Mr. William Cullen of England. He created by evaporating diethyl ether, right? He created this effect by evaporating diethyl ether. He used a pump and it created a small amount of ice, which is um, cooled using the heat exchanger through evaporative cooling of this diethyl ether. Um, this is generally regarded as the first demonstration of artificial refrigeration, but it cannot become a practical device, right? Because um, you cannot just keep evaporating diethyl ether into the atmosphere or, um, you know, without a way to recycle and create a closed cycle, all right? Need a closed cycle. This is not a closed cycle. So it was not a practical device, okay? You cannot produce ice or cooling effect continuously. So the first closed cycle idea um, came from Mr. Oliver Evans, but this was not a working device. He just created a concept. So his concept was very similar to what you have today in your house. This is the concept that is behind modern refrigeration, right? And this is a term you will see throughout this course, vapor compression. So he observed that, okay, you draw a vacuum to create evaporative cooling, but then um, he also figured out a way to make sure that that evaporated um, refrigerant or evaporated working fluid has to be brought back to liquid. Okay, so the ether has to be brought back to liquid. So he figured out a way to condense that from vapor to liquid and then uh, raise its pressure again to compress and then expand again to evaporate. Okay, so he created all these steps that are there in modern refrigeration. A few years later, Jacob Perkins developed the first practical vapor compression system in 1834. It had a hand-operated compressor machine working on either, um, and it's also assumed that he got the idea from Evans. So a lot of people consider Jacob Perkins to be the father of modern refrigeration. Um, in 1851, John Gorey developed an air refrigeration machine. In this case, there is no evaporating effect, right? This is a gas cycle refrigeration where there is no liquid, it's all air. Air was compressed and expanded using two pumps to drop the temperature of the expanded air below freezing. And in 1859, Ferdinand Carré, a French inventor, developed a gas absorption refrigeration system. Technically, this is not a full mechanical refrigeration system because it primarily uses heat to drive the system. But it does have sometimes, not all devices using this method, but most of or some of the devices that uses this method do use mechanical pumps. So it could be partially considered as part of the mechanical refrigeration history. So you can see it was from 1700s to 1859, not a long time compared to the previous history. That is considered the time duration of mechanical refrigeration. Okay, now let's look into some of these designs a little bit more carefully. So the first one, which is the first invention from Perkins. Um, so here, this is a vapor compression system. Okay, so you can see the pump, which is the mechanical device, and all of the design on the left is from the Perkins patent, and the picture on the right is from a device that John Hague built based on this patent. He used this patent as reference and he made it a little bit more practical device. Okay. And one thing I forgot to mention is all these devices that were part of the mechanical refrigeration, their goal was to make ice. These are all ice making devices. Okay. Um, It was not meant directly for storage of food or like a refrigerator that we see today. They were using this method to make ice, and then ice could be used for food preservation or consumption later on. So the device described by Perkins in 1834, it has these components. It had a pump, which will draw the vacuum of ether. So you can see a chamber full of ether. Okay, so you pull a vacuum here, ether vaporizes. When ether vaporizes or evaporates, it creates a cooling effect, and that cooling effect cools the water around it, creating the ice that they were looking for. All right, and once the ether, vaporized ether is pulled, it is compressed by the next stroke of the pump, and then it passes to the condensing system where it exchanges heat with the water and cools down and becomes a liquid again. And at that high pressure, it comes back here, and this valve opens, goes back in here as a liquid, and then evaporates again. Okay, so that creates a full closed cycle. And you can see that there's compression, condensation, expansion, and evaporation. So the expansion that happens here, okay, expansion and the evaporation, these two are the cooling effects. Okay, these two things are what actually creates the low temperature. Condensation and compression are basically to complete the cycle and make it a fully practical device where you can keep running it, right? To close the cycle. So these are the cooling effects, and this is to fully close the cycle. So compression and condensation brings the ether back to a liquid, and then the liquid expands and evaporates, creating the cooling, and then it completes that cycle. And this is the same method here. Here you can see it is attached to a rotating wheel, which could be drawn using either hydraulic power or from heat from a furnace or something to rotate this hydraulic or thermal power, and that can affect the pump to compress and create a vacuum to to push the fluid through the system. Okay, and you can see one additional detail that is not there on the patent drawing here is that Evans design, John Hague's design has an insulator here around the evaporator. So that means the evaporator is more effective for cooling the water because the ambient temperature will not um, cause the evaporator temperature to rise. Okay, so that's one detail that's missing in this. patent, but it was improved upon by John Haig's design. So all these designs were able to create continuous running of a refrigerated appliance and a continuous production of ice. And it was either, to be specific, diethyl ether that was used as the working fluid inside the vapor compression system. So if you look at Gorey's air compression system from 1851, you can see that the stages in the system are compression and expansion. Okay, atmospheric air is compressed, which increases temperature. Then it's cooled by using water um, and brought to a lower temperature, and then it is expanded, and it's allowed to expand um, in an insulated chamber. This expansion causes the drop in temperature. So this is the cooling effect. Okay. So in this case, there's only one cooling effect. There is no evaporation. Okay. And then this cooling effect creates chilled air, which is used to cool water to produce ice. You can see the name of the patent is also describing a device to produce ice. All right. And this is the place where the water is kept and it's exchanging heat with the air below um, to create the ice. So Carr's absorption system was unlike the vapor compression systems mentioned before. This system, like we discussed before, may not fully classify as a mechanical um, refrigeration system because external heat is the primary driver of the refrigeration process. So instead of using mechanical sources like hydropower, you can use a furnace or a gas burner to create the refrigeration effect. Some of these systems may still use a mechanical pump, which you can see here, to bring the fluid back to the generator. This is the generator from the absorber. So absorber is at the low pressure and the generator is at a higher pressure. So the pump is used in some systems to increase the pressure from the absorber to the generator. But a lot of the um, refrigerators that use absorption method today, especially the ones that are used in RV vehicles, they don't use this pump. They only need a heat source. They use other methods to achieve this transfer of fluid from the absorber to generator, which we can look at later. But one thing I would like you to focus on is, so the compression process is replaced by two different processes, the absorption and generation. Okay, and this is where the term absorption refrigeration comes from. But then again, the cooling effect is still achieved by similar methods as before in the vapor compression. It's again the evaporation and expansion. Okay, so there is an evaporator, and right before the evaporator, there's an expansion valve. You can see here. Okay, so the pressure drops due to expansion, and then the liquid evaporates. So those are the cooling effects. Okay, so these absorption, generation, and condensation, these are to complete the cycle. And in this case, in Carr's absorption system, the refrigerant or the cooling fluid is basically a mixture of ammonia and water. They're not always a mixture. At some point, ammonia separates from water in the generator and it does all the cooling. So actually, if you look at the actual cooling fluid, it is ammonia. Okay. Water is replacing the effect of compressor through absorption and generation, okay, along with the pump. So ammonia is primarily doing the expansion and evaporation and the cooling, and the water or sometimes hydrogen, if it's used, supports that process. Okay, so we'll look into more details on this later. Again, the patent that Carrier obtained in 1860 was also for an ice machine, okay, for ice making. All right. Now that concludes the history of mechanical refrigeration. And now we are going to the start of electrical refrigeration. So what created or what triggered the start of electrical refrigeration? Once the mechanical sources were replaced by electric motors, it created the start of electrical refrigeration. It's somewhat similar to going from internal combustion engine cars to now going to electric cars, right? So the motor is going from a combustion engine to an electric motor engine. Same thing here. So going from steam engines or hydropower to rotate the uh, uh, the the pump and achieving the compression through that pump, it has been replaced by motors, and the motor technology was significantly improved in the early 1900s. The first domestic refrigerator was produced by Frederick William Wolfe Jr. Okay, and it was called, or it had a name. I guess it's pronounced Domelray, and only a few hundred machines were sold. This happened in U.S. Okay, so the start of domestic refrigeration, electric refrigeration, was primarily in the United States. So it happened in 1914. Later on in 1916, the Kelvinator Company, which is currently owned, the brand is currently owned by Electrolux. Um, and there were Kelvinator refrigerators when I was growing up, but that company doesn't exist anymore, but it's a brand that is currently still owned by Electrolux. They introduced a few of refrigerators, electric refrigerators in USA, but it was not a huge success. Okay, um, the compressors were driven by belts attached to motors located in the basement or adjoining room. The motors were really loud. The compressors were also loud. Okay. The Another version of that came in 1918, and this time by Frigidaire Company. Um, and the compressor was on the bottom of the cabinet, but right next to the refrigerator. Frigidaire Company still exists, and it's owned by Electrolux. But the actual um, commercial refrigerator, sorry, the domestic refrigerator um, that got a wide popularity where millions of people purchased it was made by General Electric Company. So up until this point, these are only a few hundreds of refrigerator models. So that's really not a start of refrigeration. But the first commercial success of producing a domestic refrigerator and selling it to millions of people was done by General Electric Company. And their refrigerator is commonly referred to as monitor top. Okay, it had a a better compressor, a fully sealed compressor called hermetic compressor, um, which was on top of the refrigerator, and that's why they used to be called monitor top. So these are some pictures of these early refrigerators. This one is the very first refrigerator in 1914, um, invented by Fred Wolf. Um, and then the details are here. So it had a temperature control thermostat. It also had an automatic expansion valve for the expansion process. It had an air-cooled condenser, so no water connections were required, and the working fluid or the refrigerant was sulfur dioxide. So sulfur dioxide is extremely harmful. Okay, it's in today's world, um, there are no refrigerators that uses sulfur dioxide, especially if it has to be used inside a house. But in those days, this is the starting of the refrigeration system. The safety was not a top priority. So this is some pictures of the Kelvinator refrigerator. You can see that the compressors are driven by belts attached to motors, and the compressors were located in the basement or in the adjoining room to reduce noise. So you can think of how loud these were. So these were really loud refrigerators that it would be almost impossible for a person today to live in a house with this kind of refrigerator and that noise. It also had automatic temperature control and ice trays. So this is the first refrigerator from GE, General Electric, the monitor top. Um, there are still some functioning refrigerators um, available in the US. So you can imagine it was built in 1920s and it's still working. Um, of course, not for daily use, but it's still functional, some of these. And they also use the sulfur dioxide refrigerant. It has a fully sealed compressor, a little bit quieter than the other compressors from the competition, which made this a popular design in households. And automatic temperature control. And this set the standard for modern refrigerators. And they popularized the idea of having a refrigerator in homes. So that concludes the history side of this lecture, the history of refrigeration. Now we look into some of the applications of refrigeration technologies. Okay, so this is a comprehensive, if not full list, if not a complete list of applications. Okay, this probably covers maybe more than 90% of the application of refrigeration. So primarily, it's used for domestic refrigeration, right? Your storage of food in your household, storage of cold beverages, medicines, and other perishables in your house, right? And what is the technology that is mostly used? I would say more than 95% of the time, it's used by the technology used is vapor compression system. On some technologies, for example, some beverage coolers, um, small scale, probably medical storage systems, some of them that are not used in a mass scale, they use thermoelectric refrigeration. Okay, the energy standards require most of the devices that are used on a mass scale to have a vapor compression system because of how good they are in terms of energy efficiency. In terms of commercial refrigeration, where the refrigeration that you see in stores and display stores that are used to display perishable goods in restaurants, supermarkets, etc. Again, the primary method is vapor compression system. Some of them also use absorption refrigeration, especially if there is some waste heat available. Okay. The same goes for industrial refrigeration. The primary method is vapor compression, and if there is waste heat available from a generating plant, then absorption refrigeration can be powered using that method. So basically, industrial refrigeration is for cooling and freezing large-scale industrial processes or equipment. Then you have seen refrigerated trucks, and you also see fruits and vegetables and other food items transported across the country from one province to the other or from one country to the other. So how do we preserve such items in transport? So you have refrigeration systems that are built inside these transportation systems. So the trucks may have air conditioning in their carriage areas. So in this case also primary system is vapor compression. There are other additional methods too. Okay. Electronics cooling. Primarily you would have seen a lot of heat pipes and a little bit of thermoelectrics inside systems. More than energy consumption, the concern here is the size of the system. You want a really small footprint, a small system that can fit inside your electronics devices. One of the problems with vapor compression systems is it's not easy to make them small. So in such situations, you use alternative methods, air cooling, liquid cooling. Uh, but there are some systems that do use vapor compression, some electronics, for example, some cameras, thermal cameras, that need cooling. I've seen that they use a small scale vapor compression system. Medical refrigeration. This require really low temperatures, okay, for storing some medicines and vaccines and biological samples. You need much colder temperatures than what you need for storing your food items. So such systems um, use both variations of vapor compression system with multiple stages, for example, and cryogenic refrigeration systems to achieve those extreme low temperatures. Ice making. You've seen a lot of ice makers in stores and restaurants. Um, there are some small ice makers that could be used in houses. Almost all of them work on the principle of vapor compression. Okay, and you can see a lot of other applications here. If you look at all the applications, majority of the time the technology used is vapor compression, and it all goes down to the first invention that was done in 1800s by Oliver Vance. So 1805, when the first concept was developed of creating using the evaporative cooling and making a complete cycle, it's we are still using the same, essentially the same method, um, more than 90% of the time throughout the whole world. And then some special cases like aircraft air conditioning uses air cycle system. Okay, this is similar to the system that was developed again also in the 1850s. Okay, so the gas cycle refrigeration system. So the aircraft refrigeration is based of this. In this case, there is no evaporation, it's compression and expansion of air. Okay, and aircraft is a specific example where that is practical, even though it's extremely energy inefficient. But other safety and convenience constraints or requirements uh, makes this a better option over vapor compression systems, because such vapor compression systems would create a much heavier load for the aircraft in addition to other creating additional safety constraints. You might have also seen dehumidifying devices that are not exactly for cooling, but to condition your air to remove moisture from the air. Again, primarily vapor compression systems. There are some thermoelectric systems also available in the market. Now, let's compare some of these technologies in terms of their energy efficiency. So the energy efficiency is typically noted by this term COP, which is basically the coefficient of performance. Okay, the coefficient of performance is basically defined. Any efficiency is basically defined what you get out of the system to what you're paying for it to the system or inputting to the system. So if you look at it that way, what we are getting out is the cooling effect, or you can define cooling in terms of joules or watts if you're looking at the cooling power. And then the input can also be in joules or power. depending on how much energy you're paying to cool it. So if you look at the vapor compression system, you get a lot more cooling power than the power you're putting into the system. In terms of absorption system, that is much lower than the vapor compression. Okay, cryogenic even lower. Thermoelectric also somewhat similar. Air cycle refrigeration also low. Okay, so this is the main reason why vapor compression system is so popular. There have been so many efforts with coming up with, for example, solid state refrigeration systems, uh, magnetocaloric, elastocaloric. So many other technologies are still being investigated, but none of them come close to being practical and consistently deliver good performance as a vapor compression system. And vapor compression system itself is studied so well that there are so many different variations, so many different fluids that can be used, um, so many different arrangements of the cooling technologies that, and also control methods that it's further improving its coefficient of performance, right? Now let's further look into the temperature range of some of these applications, right? So if you look at beverage and wine coolers, etc., you're looking at 7 to 18 degrees C, 1 to 18 degrees C, 1 to 10 degrees C. Okay. But when you start storing your food in the refrigerator, you don't want to go above 4.5 degrees C. Um, and when you talk about blast chillers, you're going in the range of minus 18 degrees C to 3 degrees C. So it quickly cools. Okay. Then ice makers for soft ice is almost close to 0 degrees C. It's almost melting. Then there are ice makers that are typically used that are very close to minus 18. The freezer in your refrigerator is also minus 18 to minus 23. Okay, so as you keep going down, you can see that once you reach the medical grade um, devices for storing vaccines, etc., they need to be stored at much colder temperature than the freezer in your house. For creating frozen packages for quick freezing, you need a blast freezer. That's also cold. But storing really um, perishable vaccines like the COVID mRNA vaccines um, and some biological samples need extremely low temperatures, up to minus 86 degrees C. And even further, for storing even smaller biological samples like reproductive materials, um, for example, you've heard about eggs being stored for future use. Such things, such items require extremely low temperatures of minus 150 to minus 196 degrees C that you need cryogenic technology. Okay, so let's look at some of these items that we discussed. So these are some examples of beverage coolers. Uh, these are some examples of ice makers. You can see this ice is basically very soft and it's stored at 0 degrees C, but typical ice is minus 18 to minus 9 degrees C. This is not easily eatable or chewable, but this is chewable. So there's so much to learn in the ice technology um, that, that's a different topic altogether. But you can see the temperature ranges. In your house, the freezer goes from minus 18 to 23, and some refrigerators have freezer on the top, some have freezer on the bottom. There are some that are on the sides too. But anyway, the freezer is much colder than the refrigerator portion, 1 to 4.5 degrees C. Okay. And then ice creams, um, they require much colder temperatures for storage than a regular freezer. So that's why the ice cream stored in the store, they have a good texture, but when you put in your freezer in your house, they may not have the same texture as what you'd see in the ice cream store, okay, because the temperature ranges are slightly colder. And this is an example of a blast chiller, where blast freezer, where you quickly freeze your food items for um, later use, and then you seal them in a bag and then you use it for later. These are some example of medical refrigerators, ultra-low freezers for storing biological material. All right, so that concludes this first lecture on history and applications of refrigeration and air conditioning. Thank you.